series of chance talks, sadly, which today will be on Bayesian networks and information intelligence.
Thanks very much. Well, it's been great speaking here. I'm giving little tastes here and there of how to use networks and category theory to study various interesting subjects deliberately other than the theme of the QMAC group that invited me. So in other words, not quantum mechanics or quantum computation or even really computer science, but all sorts of other things to which the same techniques potentially apply. So this network here is an example of a Bayesian network that shows different factors, different variables involved in the coral bleaching crisis that we're facing. Coral reefs getting bleached partially due to global warming. So it's an example of a Bayesian network, which I'll talk about at the end here. So last time I started introducing the theme of stochastic mechanics, where we work with good old-fashioned probabilities instead of quantum amplitudes. And I think there's a lot of room for exploration there because for some reason the sophisticated people who know about category theory like to apply it nowadays to quantum mechanics, but not so much to probability theory. So there's room for exploration. So here's the kind of thing I'll be looking at. Suppose you have two finite sets. You might think of them as states, sets of states of some system. Then a stochastic map maps each element of the first set, x, to a probability distribution on the second set, y. So what that means is that for each pair of elements, one in x and one in y, we get a real number such that if you fix a particular x and look at those numbers for all points y, you get a probability distribution. So it's a generalization of a function that instead of sending a point to a single point, sends a point to a probability distribution of points. And so those numbers would be the probability of the output y given the input x. So a little bit more legalistically, what we mean is that for any point x and any point y, we have a non-negative real number such that if you fix a particular x and you sum up these numbers over all choices of y, you get 1, so that they represent a probability distribution on the set y. So this is a very basic category here, the category of finite sets and stochastic maps between them, which is good for understanding random processes, processes where what you do doesn't determine what happens, but only determines a probability distribution of what might happen. Why is it a category? Well, it's a category because you can compose stochastic maps. So a stochastic map is really a matrix of numbers, so you can compose them by doing matrix multiplication. So G composed with F will be a matrix that tells you the probability that if you start at X, that you wind up at Z, and this is the formula for matrix multiplication, but it has the meaning that you look at the probability. Sorry, these numbers are screwed up. Sorry, that should be an X there. So you take the probability that you start at X and go to some intermediate state Y using the stochastic process F times the probability that you go from that intermediate state Y to the state Z using the stochastic map G, and you sum over all intermediate states. So of course, we all know about matrix multiplication, and that's all this is, but it's good to remember that Heisenberg reinvented matrix multiplication all on his own when he was inventing quantum mechanics, where instead of probabilities, he was thinking of matrices of complex numbers, and he was trying to imagine a new description of the world where a quantum process would be described by a matrix of complex numbers, and the meaning of those matrix entries would be the amplitude that starting in some state X, you wind up in some state Y, and he invented this formula as the obvious formula for how you compose those quantum processes. And then his thesis advisor, Bourne, told him, "You've reinvented matrix multiplication. Go read a book." Which is fascinating, of course, because one thing that means is that even a very good graduate student in physics in that era wouldn't have learned matrix multiplication in the normal curriculum, whereas by now it's considered standard. So maybe there is progress in the world after all. So now we're just reusing that in the much simpler situation of probabilities. With quantum mechanics, the big question was, well, what do these amplitudes mean? But in probabilities, there still are questions what they mean, but they're less mysterious. So we got a category, which I'll call fin stock, fin for finite, because you can imagine an infinite version of this as well, and stock for stochastic maps. Stochastic is just a fancy word for random. So finite sets are objects, and stochastic maps between them are morphisms. And whoops, this is a really bad slide. There should be little wiggly arrows for stochastic maps. So that wiggliness means that it's random. Because there are also actual functions, of course, from one finite set to another that have no randomness. So that's what I'm saying here. If you give me a function from x to y, it gives you a stochastic map where each point in x gets sent to a probability distribution that's completely concentrated at one element of y. 0 everywhere except at that one point, and 1 there. So that means that you have a kind of inclusion of the usual category of finite sets and functors into the category of finite sets and stochastic maps, so a functor between them. So it's nice to be able to play back and forth between these two categories. So what can we do? Well, very basic thing we can do is look at stochastic maps from a one-element set to some other set. So, in category theory, you choose your one-element set. Don't tell anyone else what the element is, because they don't really care about that, and you just call it the one-element set. So a stochastic map from the one-element set to any other set, well, what would it be? It would assign each element of here a probability distribution on here. So there's only one element in here, so it would just be a probability distribution on x. So a probability distribution is the simplest case of a stochastic map. And very often in probability theory, we're interested in a finite set of states with a probability distribution on it. So if it weren't finite, we could call that kind of thing a measure space, or a probability measure space, more specifically. But here it's a finite set. I don't know, this is a horribly long term for such a simple thing, and it's even confusing, but I'll call this a finite probability measure space, where finite applies to the fact that the space is a finite set. There's also something called a finite measure, but that's irrelevant, okay, for what we're doing. Anyway, those things, though I need a shorter name for them, are very basic. So if you flip a bunch of dice, you have a set of possible outcomes, you get one of these things, a finite probability measure space. So I want to think about these things, and of course in probability theory people have thought about these things for over 100 years, but I want to think about them using the tools of category theory to look at things in a new way. So we're leading up to that. So there's a category of these finite probability measure spaces. So here's a finite probability measure space, a probability distribution on x. Here's another one, so we're getting a probability distribution on y. One kind of thing you can look at is a function from x to y, which when you compose it with p, the probability distribution on x, gives you q, the probability distribution on y. Remember, functions are special cases of stochastic maps. So I can compose a function with a stochastic map, and in general I'll just get a stochastic map. So it makes sense, it parses to say that doing p and then f is equal to q. And if you figure out what that is, what it means for this triangle to commute, you see that it means sort of the only thing you might have guessed, the only sensible thing, which is that it's a function which carries one probability distribution on x over to this other one on y. So if you unravel the matrix multiplication involved in composing stochastic maps, and if you turn this function into a matrix of zeros and ones, because it's a deterministic stochastic map, work it out, and you see that the equation for the matrix multiplication boils down to this equation here, which just says the probability of an outcome y with this probability measure is equal to the sum of the probabilities of the elements of x that get sent to that outcome. So this is what you could call a deterministic way of processing random data. So for example, you might flip a bunch of coins, get a bunch of random bits. So this would be a set with some probability measure on it. And then you might do something like count the number of heads you got. That would be a deterministic map from the set of n tuples of bits to the set of natural numbers, or maybe numbers between 0 and n, to make it finite. So that's a deterministic way of processing that random variable to get a new random variable. This new random variable would be the probability distribution on the numbers from 0 to n. So the probability distribution saying the probability that you had a certain number of coins land heads up. So that's a very widely studied category. If you've ever studied Markov chains, finite Markov processes, that's what you're building upon there. And if you haven't studied it, it's still easy to understand the idea of taking some random numbers, performing a deterministic calculation on them, and getting some new random numbers. So you can compose those kind of things. Those kind of things, I forgot to say, people call them measure-preserving maps between finite probability measure spaces. You can compose them. So if I have one of them here, F, and another one here, G, I can compose them. I get this new composite function here. And because this first triangle commuted and the second one commuted, then the whole big triangle commutes. That's the way it works in category theory. So you get a category where you have this new form of, new kind of morphism and a new way of composing them. Finite probability measure spaces are objects, and measure-preserving maps between them are morphisms. So you can think of these objects as a set consisting of states with a probability for each one, and these processes here, morphisms, are not random. They're actual deterministic functions carrying one random variable to another. You can also do all sorts of other things, right? You can say, why are you making these lines be straight? Why didn't you let those be stochastic too? And the answer is, well, I just feel like studying this today, but the other thing is very interesting too. There's a reason why I'm studying these deterministic maps. There's certain properties that they have. So here's what I want to use this way of thinking to study. So there's something famous called the entropy of a probability distribution. So if I have a probability distribution on a finite set X, I can perform this obscure summation here, where I take each probability, multiply it by the logarithm of itself, add them up, stick a minus sign on just to make it more confusing, actually to make it non-negative, and that's called the entropy. And sometimes it's called the Shannon entropy, to be more specific. Sometimes it's called information. Shannon sort of reinvented this concept, especially with attention to these finite sets, but it had already been present in physics. So Boltzmann and Gibbs had defined the concept of entropy in physics, where very often the set X wouldn't be finite, but the sum becomes an integral. And they invented that concept to understand the earlier concept of entropy that people got by studying heat, thermodynamics. So now it's clear to those who've thought about it enough that all these different versions of entropy that I just mentioned are really all one and the same, and if we restrict it to the case of finite sets of outcomes, this is all you need to know. This is the formula for entropy. But that's not really all you need to know, because what you need to know is why should we care about this function here? This is a funny looking thing. So what's so great about it? Well, for starters, let me just tell you the stuff that everybody already knows. So this is a measure of how evenly spread out the probability distribution is. If it's maximized, that is, when all these probabilities are equal. So if your set has n elements, all those probabilities being 1 over n will maximize this. It will be minimized if this probability distribution is 0 everywhere except at one point. I have to tell you what 0 times the logarithm of 0 is for that to make sense, so I'll tell you it's 0. So don't question me there. I mean, if you want to take the function p log p, which is clearly defined for positive values of p, and define it for 0, you want to take the limit as p goes to 0, and you get 1. Sorry, you get 0. So, did I say 1 first? It's 0. So if your probability distribution is 0 everywhere except at one point where it's equal to 1, you get no entropy, no randomness, complete determinacy. Another way to think about it is, a more precise way to think about it ultimately, once you know what these words mean, is it's the average amount of information that you would learn if someone tells you a particular element of the set X, if beforehand all you had known was that it was randomly distributed according to this probability distribution. So you could say it's the expected amount of information that you will learn when you discover the value of this random variable. Roughly speaking, the logarithm is a way to turn, minus the logarithm, is a way of turning probabilities into measurements of how much you learn when you find out something that has occurred that had probability p sub x of occurring. So for example, if I flip a coin, and then you start out only knowing that it has a, say you know it's a fair coin, so you start out knowing it has a 50% chance of coming up heads and 50% chance of coming up tails, then log of 1/2 or minus log of 1/2 is how much you'd learn when you found out whether it was heads or whether it's tails. And this px out in front here is averaging, so it's a weighted average where we weight by the probabilities. Let me show you an example of that. So here it is. So you flip a coin. So your set consists of two possibilities, heads and tails. And let's suppose that the probability distribution is maximally flat. So both events have probability 1/2. Then the entropy is given by the formula, by the sum there, works out to be the logarithm of 2. Well, people who work in entropy often like to use logarithms base 2, so they would call that 1 bit of information. But sometimes people like to use logarithm base e, the natural logarithms. So then you'd say this is logarithm 2 nats of information. But people love the word bit, so we say 1 bit of information. So each time I tell you the answer to a random coin flip, you get 1 bit of information. But suppose you were sure, suppose you knew ahead of time that this coin was grossly unfair, it's a lot heavier on one side, or maybe my way of flipping it involved holding it in the air and just setting it down so that the heads was up. So then you would know for some reason that the probability of it landing heads up was equal to 1. So in that case, when you find out the answer, yes, it landed heads up, you learn nothing at all. You're sure ahead of time. And so here we get this, and you see why 0 log 0 had better be defined to be 0. So that's how it works. And then, of course, for intermediate situations, the entropy would be intermediate. So this is just standard stuff that people are supposed to tell you when they tell you about entropy so that you get some feeling for it. But none of the stuff I've said so far completely pins down the concept and proves that the formula has to be exactly what I wrote down, the usual formula. So why do we use that usual formula? So I want to use a category theoretic point of view. So instead of focusing on the entropy of a particular probability measure space, I want to focus on the change in entropy caused by a measure preserving map. I'll call that the information loss of the measure preserving map. So it's the amount of entropy that you started out with minus the amount of information that you're left with after you've applied this deterministic process to your original random data. Like, for example, instead of telling you whether 10 coins landed heads up or heads down, which would be this, I could just tell you the number of coins that landed heads up. That would give you a random variable on this other set. That would have less information than telling you which coin landed heads up and which landed heads down. And so there's a general fact, it's a consequence of something even more general called the data processing inequality, which says that this is always greater than or equal to 0. So it means, in this case, that if you apply a deterministic process to random data, you can only lose entropy. You can only destroy information. If you've learned about the second law of thermodynamics, this should make you nervous because this sounds exactly backwards. So there's a famous law of thermodynamics that says that under some circumstances, which you are never told, the entropy always increases. Okay, so this is exactly the opposite. Okay, this is saying that if you apply a deterministic process to random data, the entropy always decreases. So it's not incompatible with the second law of thermodynamics. It applies under different situations than the second law. And you can also actually write down a kind of category theoretic way of thinking about the second law, which I definitely want to do more of in the future, study more detail in the future. But that's not what's going on here. It's sort of the opposite side of things. That's why this subject is confusing. Also because there's that minus sign in the definition of entropy. So you can easily get mixed up about what's big and what's small. But anyway, what's nice about this information loss is that it has a very simple behavior under composing two measure preserving maps. Oh no, okay. I guess we'll take a break. Sorry, had a little break there for you to ask questions and think about it. So I was just pointing out that we have this concept of information loss of a measure preserving map, which is just change in entropy from the initial random variable, initial probability measure space, the same thing, to the final one. But that is just sort of set up so that it very obviously gets along with composing maps. So the total change is the sum of the change over the two steps. So we get that this information loss converts composition of measure preserving maps into addition. Now if you're a category theorist, you'll immediately think, aha, that's a functor. A functor is something that preserves composition. So here, information loss of a composite is some kind of composite of information losses. However, you'll notice that composition here is going under the name of plus. So if you're a category theorist, you'll immediately think, okay, there must be some category lurking around here where composition goes under the name of addition. And indeed, there is a famous category of that sort. Namely, there's a category with just one object and the numbers from 0 to infinity as the morphisms from that object to itself, where composing two of those morphisms is just addition. So you may think of this as a devious trick to turn a perfectly simple thing into a category, and in some sense it is, but it's not really devious. Just whenever you have any sort of associative operation, it's probably composition of morphisms in some category. And so this is the category which I will call 0 to infinity. So here it is. There's a category that has just one object. Don't ask what it is, so I'll just call it star. But the meat is the morphisms from that object to itself, which will be the non-negative real numbers, and addition is composition. And so what we're getting is that information loss is a functor from finite probability measure spaces to this category. So when we're saying that, that's a way of saying that this is a way of summarizing information about finite probability measure spaces and about the measure preserving maps between them in some simpler category. This simpler category has just one object, so all the different objects here are just getting sent to that one object. So in some sense, we're completely throwing out everything about the objects by means of this functor. But the meat, as I say, is in the morphisms. There are many different morphisms in here, which will have different amounts of information loss. And here we're summarizing how much information loss we have by means of a convenient category, the non-negative numbers. That's a good category for measuring amounts of stuff. So the question is, okay, great, so you've managed to make it sound complicated and say it's a functor, but where it gets interesting is, can you characterize this functor? Can you use this language to say that this information loss functor is the only functor, or maybe the only functor that has a couple of properties? And it is. It's convex linear, which I'll explain, and it's continuous, and up to a scale factor, up to a rescaling, it's the only functor with those properties. So this is giving us a way to say what's so great about entropy. So let me talk about convex linearity and then continuity. So there's a way to take convex linear combinations of finite probability measure spaces. Convex linear combination is a linear combination with you're taking, for example, a combination of two things, and the coefficients are numbers between 0 and 1 that add up to 1. A special type of linear combination. But here, we're doing something a little fancy. We're taking a convex linear combination of two finite probability measure spaces, which I'm now writing this way. So it's a finite set and a probability measure on it. And so how do we do that? Well, I need to get a new finite set with a probability measure on it. And so for the finite set, I'll just take the disjoint union of those two sets, x and y. And then I need to put a probability measure on it. And I'll just take c times the probability measure that's on x, and 1 minus c times the probability measure that's on y. That will, again, be a probability measure because we know that all these numbers in p add up to 1, and all these numbers in q add up to 1. So if we multiply them by these numbers, then the collection of all of them will add up to 1. So the idea here is that we think of a finite probability measure space as a set of possible things that can happen with different probabilities for them happening. And if I have two of those, I can combine them into a bigger one by means of flipping a coin that has probability C of landing heads up. So I could either have some random selection of sandwiches I could serve you, or some random selection of different kinds of pasta that I could serve you. But if I want to combine those choices, I could first flip a coin that's a 2/3 probability I give you a sandwich, which I select according to the probability measure P. Remaining probability, I select an order of pasta. So it's just the most very sensible way to combine probability measure spaces into bigger ones. And you can also define convex linear combinations of morphisms. So if I have a probability preserving map and another one, I can get a new one, which I'll call convex linear combination of those two. And this is the most long and disgusting formula in the whole talk, but it's almost contentless because it's just going from the obvious convex linear combination to the obvious one. And the definition of it is completely pathetically obvious. This is just a function from this disjoint union of x and y to the disjoint union of x prime and y prime. And what is it? Well, it's just the function that's equal to f on x and g on y. So that's just the only way you could define things for morphisms. In category theory, whenever you do something for objects, you want to do it for morphisms as well, to make it be a functor, fundamentally. And so the point of this is that information loss has a very interesting property. It's convex linear. So here what I'm doing is I'm flipping a C-weighted coin, a coin that has probability C of landing heads up. And I flip that coin, and then using the result, I either apply some deterministic process F to some data, or some deterministic process G to some other data. How much information is lost? Well, it turns out that it's exactly the simplest thing you might hope for. It's kind of a linearity law holds. Checking that is not so obvious. The reason is that the entropy of one of these mixtures of probability measure spaces, convex linear combination of measure spaces, turns out to be given by a fairly simple formula, which is you take the entropy of the first one, multiply it by C, the entropy of the second one, multiply it by 1 minus C. But that's not all. There's a little more entropy in there due to the random choice involved in this coin flip, and that is really just the entropy of the coin. And so this is the formula for how entropy works when you do convex linear combinations of objects. But then information loss is a change in entropy. And so when you calculate information loss, you do a formula like this minus another one. And so this coin flip thing cancels out, and we're left with just a linear law. So it's simpler, actually, to think about the information loss of a process rather than the information in a probability measure space. It is a simpler law. So it's convex linear, and information loss is also continuous. So I don't want to rake you over the coals of this in too much detail, but there's a way to make these things, fin prob and zero infinity, which are categories, make them into topological categories. A topological category is just a category that has a topological space of objects and a topological space of morphisms, where everything, all the maps involved in the definition of a category, mainly composition, are continuous. So, all of that's a fancy way of saying that we all know what it means to change a number from 0 to infinity a little bit. You can also guess what it means to change a finite probability measure space a little bit. You have some set, a bunch of probabilities on it, you can change those probabilities a little bit. And so information loss is continuous. If you change something over here a little bit, the amount of information loss gets changed a little bit. The reason why we need this continuity, the reason why we need to talk about it, is that in the theorem that I'm about to state, it really wouldn't be true if we didn't impose this extra condition of continuity. So here's the theorem. So together with Tobias Fritz and Tom Leinster, I proved the theorem that any continuous convex linear functor from finite probability measure spaces to numbers from 0 to infinity is a multiple of the usual information loss. So in other words, there's some constant alpha such that if you give me any morphism over here, it gets mapped to alpha times the information loss, where this is defined using the formula for Shannon entropy. So that's a really nice theorem, in my immodest opinion, for the following reason, that the assumptions here, convex continuity, some kind of niceness assumption. Convex linearity is just a kind of linearity assumption. Being a functor, we saw, means that when you compose morphisms here, it goes over to the sum of numbers here. So those assumptions all have a kind of linear flavor to it. They only mention multiplication and addition, and are linear in character. But from these assumptions, we're getting that the information loss has to be given by this formula involving p log p, which is a sort of weird-looking function. It's not at all linear looking. So it's not obvious, I think. So I won't give the proof, but I'll just say that there's an easy part of the proof, which is to show that any functor like this really has to be measuring some kind of change. That is, if you have some measure-preserving function g, the functor has to be of the form something about the probability measure space you started with minus something about the one you ended up with. So there's a quick little calculation you can do to check that. And then the hard part is to show that that something, which I'm calling phi, really is the thing we know and love. And you get that by repeatedly using the axioms over and over again, and then using continuity to show that this formula holds not just for a dense set of probabilities, but for all of them. So I won't really give the proof, but you can just click on that blue thing and you'll get the proof. So there's some generalizations of this, which I want to zip through, I guess. So, in fact, there are other ways to make this category into a category in which convex linear combinations are defined. So there's an abstract definition of a convex structure on a category. There's sort of the obvious one, where you take the obvious way of taking convex linear combinations of numbers, but there are other weird ones, and they're completely classified. They depend on a parameter. And so it turns out that if you use those and then demand that this functor be convex, linear, and continuous, you get other weird notions of entropy, which are in fact already known. So Salas studied a kind of entropy given by this other bizarre function here that depends on a parameter beta, which you can check using L'Hopital's rule. You can check that it reduces to the usual entropy in the limit as beta goes to 1. So this sort of explains that these other non-standard entropies really do fit into the framework. If only certain people are interested in these non-standard entropies, and so I don't expect that most of you care about that, but anyway, it's true. Something that's a little more, less of a specialist kind of interest here is that entropy is a special case of something called relative entropy. If you have two different probability distributions, P and Q, on a finite set, there's a concept of the information of P relative to Q. And that has the following meaning. It's how much information you expect on average to learn if you had previously thought that the correct probability distribution of the outcomes was Q, and then someone tells you, sorry, no, it's really P. You might do experiments and discover P. How much information do you learn when you change your mind in that way? So it's a generalization of ordinary entropy that in some sense is really more fundamental actually than ordinary entropy. It can be infinite, among other things. It can be infinite if you thought that something was impossible that had probability 0, and then someone says, no, it can happen. So then you're very, very astounded and you gain an infinite amount of information. So there's a category theoretic characterization of this thing too. So it uses just a somewhat fancier version of the category we looked at before. So here's a morphism in this fancier category. So we have a probability measure space, another one, a measure preserving map going forwards, just as before. But now we have this other thing, a stochastic map going back, which has the property that if you go back and then forwards, you get the identity. What's that thing going back? It's a hypothesis. It plays the role of a hypothesis. So what I mean by that is you should think of this as some kind of system you're measuring, and this as the measurement apparatus. And suppose the measurement process is completely deterministic. So any state of your system here gets deterministically sent to some reading of your measurement apparatus, like the position of a dial. But that you measure may not completely be enough to determine what the original system was doing, but you could make a guess about what it was doing. And that's what this S does. So for any measurement reading, you guess a probability distribution of states on the system. And this is a kind of consistency condition. It says that if you make that guess and then go forwards, you do indeed get back where you started. And so this is a category where you should think of the morphisms as being a measurement process together with a hypothesis about the system you're measuring. And that's a situation where you can talk about relative entropy, because in this situation here, there will be a probability measure on the system X. We could call that like the true probability distribution of states of X. And then there'll be another probability distribution on there, which is what you get by taking the probability distribution of states of your measurement apparatus after you've made the measurement, and then use your guess. So compose that stochastic map with that stochastic map to get another probability distribution on X, which is your guess about the probability distribution of the states on X. So there's the truth, and then there's your guess about the truth. And that's sort of the situation where relative entropy is important. You can then suppose someone tells you the actual truth, then you would learn something. So we can talk about how much information you'll gain if you learn the true probability distribution of states of the system, given your guess, your best guess. So sometimes your best guess is right. So sometimes when you take your probability distribution of states on Y and you compose with your hypothesis, you actually get the exact correct probability distribution on X. And in that case, it turns out that, as you might expect, this relative information is 0. So if your guess about something is right and someone tells you the truth, you don't learn anything because you already knew the truth. So that's good. So there is this category that I mentioned before, and then there's this category which for some stupid reason is called FP, which are the ones where your guess was right. Morphisms where your hypothesis is optimal. And we know relative entropy vanishes on that. And so then the theorem, after this long build-up, is very short. So, same kind of hypotheses. Any continuous convex linear functor, but now from this category where the morphisms are a measurement process together with a hypothesis, to this category here, which is like the one we saw before, but now we actually need to include infinity as a possible outcome. So any functor like that vanishes on the morphisms where your hypothesis was exactly right has to be a constant multiple of the relative entropy. This theorem is tons harder to prove than the first one, actually. I would have given up, but Tobias kept digging away and proved it. So if you're the sort of person who likes to outdo other people, please do that, okay? So click on this blue thing and find a better proof than we have of this. I feel there should be one, but it couldn't find it. But anyway, the statement is nice and simple. Okay, so I should stop pretty soon. I just want to say something about a somewhat different topic. So, Brendan Fong here has written a paper called Causal Theories, a categorical perspective on Bayesian networks. He's a show-off, so instead of using this category thin stock that I've been talking about finite sets and stochastic maps, he was actually mainly focusing on one where you don't require the set to be finite, but let's not worry about that, because we don't have enough time to talk about that. I want to talk instead about what he did with it, which is different than I've been talking about so far. It's studying Bayesian networks. So, a Bayesian network starts out being a picture like this. So you have a bunch of different variables, how much it's raining, how much it's sun there is, so on. And these arrows, edges, which represent causal relationships. Something could cause something else. So what we've got here is a directed acyclic graph, a graph where the edges have directions and there are no cycles. And that's all we've got. That's a Bayesian network. But you intuitively think of each vertex as being some variable, and you think of each directed edge as a causal relationship. And the idea is you want to think about models of the world based on this Bayesian network. That is, so far, I have not associated a particular set to A, but you might want to. You might want to say, okay, it's either raining or not, so I maybe want to have a two-element set of those two possible conditions, raining or not, or maybe how much it's raining, use a 100-element set. So we might like to take this model here and instantiate it in some actual sets and functions, or maybe stochastic maps. And so, roughly speaking, this is what Brendan does. Actually, this, he didn't say he did this, so I'm sort of reinterpreting what he did after reading it. Maybe it's true, maybe it's not quite true. I think it's true. So, I think what he did is start with this directed acyclic graph and forms a category out of it, which is a category that has finite products in the categorical sense. It has one object for each vertex and one morphism from a product of those objects to some other object. Whenever the AI are all the parents of B, that is, all the guys that have edges going to be, all the guys that have edges going to be. So, for example, here, if I pick D, this could be like how happy you are in England. It seems to be mainly based on, what did I say, how much it's raining, and then how sunny it is. So both of those affect you. Of course, whether it's raining affects how sunny it is. But we will put in we'll put in our category a morphism from A times B to D, representing the causal relationship of these two factors on your happiness. So we build a category with finite products out of those generators. And in particular, if there are no parents, if you have a node that has no edges going to it, that means a morphism from the product of no things. So that's called the terminal object, B. Notice that subtlety. And so that's what he calls the causal theory described by that graph. So it's a theory in the sense of, Levier, who liked to think of theories as being categories. And then the point is that a model of that theory can be described as a functor, which basically is preserving, it's a symmetric monoidal functor, meaning preserving products, roughly speaking, which sends these abstract variables here to actual sets, and sends the morphisms to stochastic maps. So there's some stochastic map from the weather conditions to your happiness. They don't determine your happiness, but they influence your happiness. So I'm starting to use jargon the way people do at the end of talks. They say, okay, I'm sick of trying to really explain things. I'm going to use more words that I didn't define. Okay, but if a lot of you know some category theories, I don't feel too bad about that. But then unpacking that slightly, what it means is that we get a finite set for each vertex, each variable, and then we get a stochastic, we get various things. As I said, if somebody has no parents, if a vertex has no parents, we get a stochastic map from the one element set to its set, and that's, as I said, just the same as a probability measure. And then more generally, if some node has a bunch of parents, we get a stochastic map from the product of those sets to get. I'm just unpacking the short thing on top. And in particular, from that we can get a random variable for every vertex, because we start out with random variables, i.e. probability measures on sets of the vertices that are the guys with no parents, and then we can propagate them down, apply stochastic maps to them to get probability measures for all the other vertices. So the idea is that there'll be some things that are sort of determined only by the gods, how rainy it is, how snowy it is, and they will have implications for other things that are affected by them, and you get a probability measure ultimately on for every vertex there. So this is a very slick way of talking about things that people already have talked about in Bayesian network theory, but I think it's a less ad hoc kind of way. And in particular, just automatically from this abstract nonsense, these random variables will automatically obey the kind of independence assumptions that people want in their Bayesian networks. So in other words, if two vertices have no ancestors in common, their random variables will be independent. They'll be what's called stochastically independent. So the idea is that the only dependencies arise from common causes. So with that brief sketch, that ends my series of talks here. And so I've been trying to outline a big bunch of stuff that's just partially worked out. We've seen how category theory connects signal flow diagrams and electrical circuit diagrams, where we are using vector spaces and direct sum as the tensor product, linear maps, which we know. Stochastic Petri nets and chemical reaction networks, two formalisms for basically the same thing, used in subjects like chemistry, epidemiology, population biology, where it's basically looking at Feynman diagram-like structures, but where processes are probabilistic rather than quantum processes. And now today, following that kind of stochastic theme, looking at Bayesian networks and seeing how information and entropy, those allied concepts, arise naturally just from this category theoretic point of view. So I'm hoping that in the future these different branches of the topic I'm discussing will fit together better. I really enjoyed giving these talks, partially because I realized how incoherent these talks were. Well, hopefully each one individually was coherent, I hope, but what I mean is that they really, I think of them as all being part of a single subject, but I wasn't able to give a presentation that made it look like that exactly. We have a bunch of different categories running around here, many of them involving random processes, but they should be integrated. And the reason why they should be integrated is because all sorts of people are studying complex systems made of interacting parts, like chemistry, biology, all the things people model with Bayesian networks, the things electrical engineers do. They're all really trying to do very similar things, but they're so focused on what they're doing that they don't necessarily step back and look at the relationships between what they're doing. And category theory is exactly designed for that. Category theory is the branch of math that lets you take a bunch of things people are doing and see them as in a common framework, and then set up lines of communication between different things, different communities of people. And so, as I said, I'm trying to ultimately do some good here with our ecosystem, which is sort of the ultimate complex system made of interacting parts, understand it, help it. This is not a request for money when I say please help. This is you click on this and you'll see all sorts of scientific projects that a bunch of people are doing in a project called the Azimuth Project, which on the mathematical side is focused on this network theory, and on the more practical side, we're trying to sift through the arguments that people are having about global warming and other ecological issues and try to get a wiki going of fairly reliable information about those subjects. So somehow that's all supposed to fit together someday. Okay, so thanks.
Thanks, John. Time for questions?
Yep.
I have a very naive question, so I'm
Good.
hoping I just got tangled up
Yeah. There.
Yeah, so can you show the whole slide?
Yeah.
Right, so given the way you set things up, I can understand why the answer is 0.
Uh-huh.
But on the other hand, it seems like you've learned something very important.
That you're right.
That you're right, and that you should stop.
That's some kind of, yeah, some kind of meta learning. So we don't have any thing in this formalism about knowing that you're right. When I write down this formula for relative entropy, which is sort of what's underlying this functor, this is the way I intuitively say it is that if you thought things were distributed according to Q and then someone tells you no, it's P, you've learned something, and this measures how much you've learned. And it's, when you're thinking about that, it's very convenient often to think of P as being the truth. Q is your opinion before you hear the truth. But there's nothing in the mathematics about that. There's nothing in the mathematics that says that P is true. Right? So P could be a lie, right? So you could learn, quote, what you thought was the truth, and it's a complete bunch of baloney. You're fooled into believing it, and you would have gained a lot of information. But there's nothing about information theory that says the information is true. It's just, obviously. Read newspapers, there's a lot of untrue information, and information theory is not mainly about that. So when I say that P here is the true probability measure, that's a very useful way of thinking about this, but it doesn't really enter into any of the calculations. And if I were being a hardcore Bayesian, I would avoid ever saying the phrase the true probability distribution, because they regard that as like a sort of a contradiction in terms.
But I guess extending your metaphor then, if there's nothing left to learn, you can stop.
Right. So, I mean, this is, you learn, you can stop learning, right? That's right.
Okay, any more questions?
There seems to be a slight conceptual difference between what people understand usually as convex combinations and these ones, because even if your sets are the same, you treat them as different. While
Right.
usually convex combination, you mean mixing together.
Right, that's right. Yeah, this is a funny thing where we've got a category, and if you give me any two objects in it, I can form this funny new object that's called a convex linear combination of them. And similarly for morphisms. And if you want to make it more detailed or fancier, there's a thing called an operad for convex linear combinations. It's just a thing that has convex linear combinations as its operations. There's a concept called a convex set, which is a set where you can take convex linear combinations of elements. So that's what you're very often seeing in foundations of quantum theory or probabilistic theories. But here what we're doing is we're letting that operad act on a category. So we can talk about convex linear combinations of objects and of morphisms in a functorial kind of way. And it's only for that way of thinking about things that you actually get this nice property that information loss is convex linear. Yeah. So it's a somewhat different angle on things.
More questions?
Yes?
Do you think the condition that your assumption that you're only working with finite sets is actually important, or just a technical simplicity?
It's going to be just a technical simplification. If you work with infinite sets, the main thing that you have to be careful about is that this can then become infinite, so it goes all the way up, including infinity. So you have to adjust the statement of the theorem, but it probably can be generalized to that. And if anyone likes analysis, that would be a great project to work on. And so it's basically that we wanted to avoid extra work. So I would presume the good way to deal with a general case is you take a probability measure space and you in some sense approximate it basically by chopping it up into chunks, a finite set of chunks, and get a finite probability measure space. And use the theorem for the finite case to boost your way up by approximations to the general case. And that's a pretty good idea in general because that kind of thing would be a morphism in your category. So you'd start out with this probability measure space that may not be finite, and then this would be the set of chunks, and there'd be this map here, which would be a quotient map, which would be one of these morphisms in our category. So then you could use the functoriality to gain information about what's going on here from these approximations. But yeah, I've been thinking that if I ever get a grad student who likes analysis, I'll make them generalize both these theorems in the way that you're suggesting.
Okay, no more questions? Then let's thank